All right, so last time we did our introduction to MSE walls, and we looked at basically the theory of reinforced soils. And that gave us some general ideas about how reinforced soils behave as a composite material. But now we're going to look at the actual design procedures for MSE walls. There's two presentations on this. I got a feeling I can't get through both of them today, but I think what would be most fruitful is we'll definitely get to the first one. And I think what we'll do is we'll get to the first one and then go straight into the second one. If we don't get all the way through it, that's fine. We'll finish it up on Tuesday, and that'll give us some time to start working on your MSE design problem, which I'll assign before Tuesday. And you all owe me the sheet pile design next Tuesday, right? Okay, excellent. All right, so let's talk about how we design MSE walls. So this first presentation is really about the components of the wall and how we characterize the components and how the components behave. So you need to identify the three main components, which are the reinforcement itself, the facing material on the wall, that's the thing you see when the wall's completed, and then the soil that's being reinforced. So those are the three main elements of the wall itself. And remember, this is our first look at internally stabilized retaining walls, and the soil, we'll go through this in a little more detail during the presentation. The soil that's being reinforced is part of the wall. We're going to distinguish between that soil that's actually being reinforced as being part of the wall and the soil that's behind the wall that's the retained soil. And we'll go through that a little later in the presentation. But that's actually part of the wall in this case. And then you need to describe these key properties that are important for the reinforcement material. And then we discussed this just a little bit in the last lesson, and we'll do a little review of what we discussed there and go on from there, but talk about how the reinforcement anchorage strength is developed, which is a combination of both friction and bearing, sort of like horizontal bearing. So you need to understand those two behaviors and how they're different from one another. For the soil that has significant passive bearing, its bearing capacity is a function of the overburden stress, and you need to be able to understand how the overburden stress affects that passive bearing. And then we talked last time about extensibility of, well, we didn't call it extensibility. We talked about the stiffness of the soil versus the stiffness of the reinforcement, and that's going to play out in our designs. And we call it, in the MSE world, they call it extensible versus inextensible reinforcement. And we're basically talking about steel reinforcement versus polymer reinforcements. And one of those is extensible or ductile or less stiff than the soil. That's the polymers and the steels. And the steels obviously are the inextensible. And it affects their pullout capacity. So we'll be talking about that. And then although most of the pullout capacities you're going to use for design are determined from laboratory testing, we want to talk about how to estimate those numbers so that if you don't have laboratory testing and you're starting a design, you can at least do some estimates of it before you get those data. And then obviously we got to be able to compute the allowable loads in the reinforcement. And then these are the key properties of the reinforced soil that are going to be important: the grain size distribution, the strength, and then its electromechanical properties. And then you need to be able to describe what facing does for us. We don't really design facing. The facing is basically commercially available stuff, with the exception of if you're doing a shotcrete facing. But you have to understand its properties. Okay, so let's go and talk about reinforcing shapes. This is a bit of a review from last lesson, but it's a good place for us to start. The reinforcement comes in really just a few shapes. One is a sheet, and the key with the sheet, the key to a sheet is that the width of the reinforcement B covers the entire width of the reinforced area. So I couldn't draw an infinitely wide block, but that's the intent of this. A bar is a cylindrical piece of reinforcement that goes back into the soil. A strip is distinguished, if I called this W, I guess that would be a good thing. A strip is distinguished from a sheet in that the width of the strip B is less than the width of the reinforced area. You can obviously have multiples of these. A grid is a grid. And then finally, there's anchors. And we're not going to talk about anchors because most MSE walls don't use anchor systems. But there have been some that have been used. So for the most part, we'll be talking about sheets, strips, and grids. Those are by far the most common geometries of reinforcement. The most common kind of bar reinforcement is if you do a soil nail wall. But we're not covering soil nail walls in this course since they're covered in the slope stability course. All right, well, let's talk about pullout resistance. So pullout is just, there's several ways that reinforcement can fail, but one is that it just pulls out of the reinforced soil as you pull on it. So it's a pretty simple concept. And we discussed this briefly last time, but we'll review it again. There's two sources of resistance to this strip being pulled out of the soil. One is a frictional resistance, which is just going to be a function of the normal stress applied to the strip and the interface friction angle. So the capacity of this strip T is just going to be the area of the strip. By then area, I mean this area, not the cross-sectional area. The area of the strip times the vertical stress times the tangent of the interface friction angle. It's not the soil friction angle, it's the interface friction angle between the material and the soil. And then the other form of resistance we get when we have a element that's not a bar and not a sheet, it's not a flat bar and a sheet, and that's passive bearing. So if I'm pulling on the element in this direction, I'm obviously going to get some resistance along the sides of the element. We call it passive bearing because it sort of looks like a bearing capacity failure in a horizontal direction. So in that case, and we talked about this last time, the horizontal bearing is going to be a function of the vertical effective stress, because the vertical effective stress here was going to provide confinement to the soil there and obviously increase the horizontal bearing capacity. It's going to be a function of the area that's actually exposes itself to bearing along each of the elements, and then obviously a function of the internal angle of friction. And it's fairly complicated, and we'll talk about that in just a minute. And for most elements, there are very few elements that use only friction, and none that I know of that use only passive bearing. So in most cases, sheets obviously use only friction, and strips use only friction, except most strips are ribbed. They're not flat strips, so they have some bearing on them. So almost all of our elements use a combination of these two things. So the way we categorize our reinforcement is based on the material and the shape. So the materials are metal, which is stiff, and when we say metal, it's almost always steel. I don't know of any reinforcement that's not steel. It's treated, it's almost always coated. We'll talk about that in a while. So this is very stiff compared to the soil, and we call it inextensible. That's just another word for the relative stiffness, but the terminology that's used in the business for the reinforcement is inextensible. When they say inextensible, they're talking about metal reinforcement. And then there's polymers, and there are a number of different polymers used for MSE walls. You don't need to know a lot about polymers and chemistry, but you need to know enough to recognize names and understand some about the behavior. We'll talk a little bit about that when we do this. If you do a lot of MSE wall design, you probably need to spend a little time understanding that. It's a really good book out by Kerner called Designing with Geosynthetics. It has more detail than you'd ever want in this, and his latest edition of it is available as an ebook for, it's in 2 volumes, but they're like $5 a piece or something like that. So, and he's like the godfather of geosynthetics. So if you'll probably want to know more about polymer behavior if you get into this a lot. But we call this extensible because it's relatively soft or much less stiff than the soil, relative to the soil. And so these are our 2 terms that we're going to be using when we discuss the relative stiffness of the reinforcement versus the soil. And then the shapes are strips, which are either smooth or ribbed. By far the most common strips out there are all ribbed. because there's an advantage to doing that. Same reason you don't see smooth rebar in concrete. We generally don't put smooth strips in soil. Grids and sheets. Sheets are not at all uncommon. But they're definitely less common than strips or grids. The grids tend to be, the grids come in both polymer and steel. The strips tend to mostly be steel, and the sheets are always polymers. It's not very common to have polymer strips that I can think of. And putting sheets of steel down is pretty expensive. We usually don't do that. All right, let's talk about how we actually determine the pullout resistance then. So as we said, this is a function of both the friction and the passive bearing within a grid. And we're going to use this formula. Like a lot of things in soil mechanics, when they get really complicated, we just take all the complicated stuff and call it a factor. And then we'll use empirical ways to get the factors. And so this is our formula. The pullout resistance, which is a force, this is going to be a force, is going to be a F star, which is an apparent friction factor. We're going to talk about why that's apparent. Even though bearing is not a frictional function, is not a frictional behavior. Well, it's a friction. It's friction within the soil. But even though it's not the normal stress times the interface friction angle, it is going to be a function of the effective vertical stress, which we talked about. And so, generally speaking, we're going to convert the bearing into an apparent friction term and just treat it all like friction from a computational standpoint. So F star is going to be apparent friction, which is a combination of bearing and friction. We'll discuss that in a minute. Alpha is a ductility factor. So this has to do with that phenomenon we talked about last time, which is how much of the load is carried by the reinforcement and how much is carried by the soil, and that's a function of how stiff the soil is versus the reinforcement. So if the reinforcement is very stiff, you're going to transfer all the load to the reinforcement. If the reinforcement's not so stiff, you're not going to transfer all the load to the reinforcement. So alpha is equal to 1 for inextensible reinforcement. So in inextensible reinforcement, we're going to have an alpha equal to 1. And in the cases for the extensible reinforcement, we're going to use alphas less than 1, because if we allowed all the load to be transferred into the reinforcement, we'd have so much displacement and it would be unacceptable. So we reduce the reduce the pullout capacity based on it's really an artificial way to put a displacement limit on a strength limit. So we really are, for our structural guys, we're really kind of convoluting ultimate limit states and serviceability limit states, but it's the way it's normally done. Sigma V is our effective vertical stress. And then LE and C are basically our areas, right? So LE is the length, the embedment length. We'll talk about later, talk about the difference between the total length of reinforcement on the wall and the embedment length. But it's that amount of the reinforcement that's actually contributing to pullout capacity. And then C is the effective perimeter. This should be pretty obvious that for strips and grids and sheets, it's 2, because you got 2 surfaces, right? You got a top and a bottom. When I derived this stuff, we were talking just about friction on one side, but you've got it on the other side too, right? So when you put a strip in, you actually get 2 frictional resistances, one on the top and one on the bottom. The only time the only time C is not 2 is if you're using bars. And then you because you calculate the whole perimeter of it. So, but for most cases, for us, the effective perimeter is going to be 2, because we'll be using almost always strips, grids, or sheets. So this is our basic formula. So in spite of the fact that we said that the pullout resistance was a function of both friction and bearing, what we're going to do is convert both the friction and bearing into a single apparent friction term, right? Multiplied by, so that if you want to think about it, this is tangent. F star is the equivalent of tangent phi interface, or the coefficient of friction if you want to think about that. It's like an equivalent coefficient of friction times the vertical stress. Alpha accounts for whether we have inextensible or extensible reinforcement, and then LE times C is just our area. Okay. So let's talk about how we get this magical F star, our apparent friction factor. So the real short version of this is the way you get FE is you put your reinforcing elements that you plan to use in a laboratory test and pull on them and measure the pullout capacity. You measure the normal forces put on there and you calculate F star from laboratory tests. So the real short version of this is you're going to use data from your manufacturers that comes from laboratory tests, but since you're not just idiot designers and our engineers, we're going to talk about where those numbers come from and how we can at least estimate it from theory. Whoops. I should point out that the material that you're going to reinforce is going to be, dependent on what your site is, and if you don't have pull-out tests with that material, it would behoove you to get tests with that material. If you have pull-out tests from a manufacturer and it's from a material you think is close enough to stuff that you're going to use in the backfill, and you've got a fairly low-risk wall, and you just want to use their numbers, that's fine. But if you're doing any significant construction, it definitely would behoove you to pay to have the pull-out tests run on the backfill material you actually plan to use. Unless you want to be explaining during the lawsuit after a failure about why you didn't do that. So, as I said, the manufacturers generally have these numbers for clean sand kind of backfill material, so that their numbers are probably good for routine design for any wall where you're going to be using the routine materials. And I think that just repeats the first one. If you're going to be using some material that's not been tested with, you definitely should be running tests. And if you got a really big project, I would probably do it even if you're using the same material, because you can definitely justify the costs. And you might actually be able to do a more cost-effective design, because the numbers the manufacturers are giving you are conservative. So there's definitely good reasons for doing your own laboratory tests on any significant project. So let's talk about how we could estimate it if we don't have that information. So the simplest way to estimate it is we're going to break F star down into a frictional component. Remember, F star is, in our equation is that the what number did I use? Remember, our equation is F star times sigma prime V. So think of F star as a coefficient of friction here for a minute. So if we're going to estimate it, we need to break it back down into its components of the frictional part, which is just going to be the tangent of the interface friction angle, and then this surcharge term, which is going to be, it's got two parts to it. One is essentially a bearing, if you want to think about it, it's like a horizontal bearing capacity factor. So it's like N sub Q in your bearing capacity equation. And then alpha sub beta is a function of how thick the transverse reinforcing elements are. So this figure comes out of the 2000 NIH manual. And there's kind of a typo in here. So let's just talk about this. This is the embedment length, LE. So this is the length of your element that's contributing to pullout. And there's two spacings here. There's a transverse spacing, which is the spacing of the transverse element. So the reinforcing force is in this direction. You have a transverse spacing. This should say S sub L, and that's the spacing in the longitudinal direction. The thing that's confusing here is this has a capital L on it, so that should be S sub L2. So this is so this part of the figure, if you want to think about it, is a cross section in this direction. So if I call this A prime, this is I'll write over here. This is A prime, and this one is a cross section in this direction, B prime. So this is B prime. So if we're looking in the transverse direction, you need to know that bearing area. And there's two kinds of grids. There's grids where you have welded wire mesh, where you have your longitudinal elements are in one plane and your transverse elements are in a second plane. So in those ones, you're going to get the full area of the transverse elements to bear in bearing. Right? That full area of the transverse elements is going to be available to generate that horizontal bearing capacity. If you look at geogrids or the polymer grids, generally they're all in the same plane, because the way they make them is they take a really thick sheet of plastic and they punch holes in it and they stretch it out in two directions. And so the transverse and the longitudinal elements are all in the same plane. So in that case, the area that's available for bearing is less than the total horizontal area. So they use this factor FB, which is the ratio of the spacing that's available for bearing. And in a geogrid where the longitudinal and transverse elements are in the same plane, that's going to be less than 1. If you just want to think about it, you can look up the numbers there, but that's all that number means. If you got a welded wire mesh and the transverse elements are above the longitudinal elements, you can bear on the entire length of the elements, so you're going to use a factor of 1. And if you got a transverse element, then it's going to be a function of the spacing and the diameter of the longitudinal grid elements. And in geogrids, they're not circular at all. They're definitely oval, like this looks. Have you all seen geogrids? And I should have brought some in today. I'll bring it up next time. How many people have not seen geogrids? Not seen. Well, I don't have any samples as well. How many people not seen any of the polymer reinforcements? All right. Maybe during break time I'll go get some and bring them in. I've got them in my office. I just didn't think about it today. So that's in the. So this is the looking in the transverse cross section. The longitudinal cross section is this way. This is the transverse spacing, and this is the case for welded wire mesh, where your longitudinal bars are on one plane and your transverse bars are on another plane. And so you have this. In this case, we're pulling in this direction. So you have this bearing capacity here, some kind of bearing capacity, but that's going to be confined by this vertical stress, and the vertical stress is going to contribute to this bearing capacity. And this comes directly out of your MSE design manual. So this is, we're not going to go through this one in detail. I just want to talk about where some of these parameters come from. So there's an, let me go back to this. No, that's not the right place for it. So this table comes out of your manual. There's an optimal spacing of the longitudinal bars, the transverse elements. If you get the transverse elements really close together, it should be obvious that you reduce the bearing capacity. And let me go back here to illustrate that. So if this transverse spacing is relatively large, then each one of these is going to act independently and generate whatever the maximum bearing capacity that one of these could generate. But obviously, if I start putting them really close together, they're going to interfere with each other, and they're not going to individually each generate the maximum bearing capacity that they could, because they're actually going to shadow one another, and you're not going to get the same horizontal bearing capacity of them. So S optimum is the minimum spacing that you can put the transverse elements, that you can have the transverse elements at, and still get full bearing off of each of the transverse elements. So if your spacing is less than that, you're essentially got inefficiencies in your grid, because you're not generating the full bearing capacity on each one of them, because they're shadowing each other. So that's what S optimum is. And obviously for strips, you don't have any S optimum. For grids, here's how you calculate the optimum spacing. And then, depending on whether your spacing is less than the optimum or greater than the optimum, this is how you calculate the capacity element. So if you have spacing less than the optimum, you don't have any bearing. So FQ is going to be, you're going to ignore FQ, and all of your capacity is going to come from the interface friction angle, and you're going to have to measure that. On the other hand, if your spacing is much greater than the optimum, you get almost no frictional resistance from bars or mats for welded wire mesh. If you think about it for a minute, there's not a lot of area in the bars here compared to the capacity you're going to generate out of that lateral bearing for a welded wire mesh. So for welded wire mesh, we pretty much ignore the frictional resistance of it, and are only going to, when we're calculating the resistance from this method, we're only going to look at the bearing capacity. Now, when we put it if we do a laboratory test and we put it in the machine and test it, we're going to measure its full capacity, however it's generated. But most of the capacity for a welded wire mesh is going to come from this horizontal bearing. For geogrids, that may not be the case. Anyway, so if your spacing is greater than optimum, you don't have any frictional resistance, you are going to get your bearing capacity, and you should get that from laboratory tests, or there are some default values. So for the inextensible grids, you can again calculate what the optimum spacing is, and depending on the optimum spacing, your resistance is either going to be dominated again by the bearing or the frictional resistance. And here, remember, we're going to use these alpha values that are less than 1. And this is in your design manual from FHWA. Okay, so let's talk about metal reinforcement now. So for ribbed metal strips, and I meant to take a picture of these. I've showed you a picture of these, but if you look at the reinforced earth, which is a proprietary method, they use strips, but the strips have little ribs on both sides of them. Actually, if you look at them, they actually kind of look like little trapezoidal areas on both sides. So most commonly when you're using strips, they are by far the most common strip method. They are ribbed. So even the frictional resistance is not fully frictional. But you calculate the frictional resistance. If you're going to estimate it as tan, we're going to use rho for the interface friction angle. And they estimate that based on the coefficient of uniformity. Which may seem, this is a completely empirical fit, and it should make some sense. If you have, as your coefficient of uniformity gets smaller, you got more and more uniform soil, right? A high coefficient of uniformity means a well-graded soil, and obviously a well-graded soil is going to have a higher friction angle, and the higher friction angle is going to have a higher interface angle. So the way you estimate F star for metal ribs is simply 1.2 times log of the coefficient of uniformity, but don't ever take it greater than to be 2. Notice this is tan phi. So that's a coefficient of friction that's actually greater, that's 2. So, what's the, that's saying you're getting more horizontal resistance than your vertical stress. These are for depths less than 20 feet. Because what's happening at depths less than 20 feet, you have relatively low confinement. Your soil is going to be dilative, right? And because it's going to be compacted, so it's going to be dense. It's going to be dilative, and you're going to because you have the ribs in there, you're going to essentially get some bearing capacity out of those, some horizontal bearing capacity, because you're going to cause the soil to dilate during shear, and you're actually going to get an apparent friction that's actually greater than, a coefficient of friction that's greater than 1, amazingly. Now, when you get to deeper depths, your coefficient of interface friction angle is going to turn into the friction angle of the soil. And why would it turn into the friction angle of the soil? Well, if you go to deeper depths and if the soil wants to shear, if that interface friction angle gets really big, it's just going to shear in the soil around it. So at depths greater than 6 meters, your friction, your apparent friction is just going to be the internal angle of friction of the soil. Because at those depths, the soil is not necessarily going to be dilative anymore, because you got enough overburden stress, even for well-compacted soils, that it may already be near it may behave as in a critical state. That is, it's not going to be neither dilative or contractive. But we'll still get a greater. If you want to think about it, we're still saying that the apparent interface friction between the material and the soil is greater than the interface friction angle, because otherwise it wouldn't fail in the soil. So if for metal grids that have spacings greater, that have spacings of the deformations, so that's I'm sorry, let me start over. For metal grids that have spacings of the transverse elements that are greater than 6, it's which is beyond greater than 6 inches, which is greater than the optimum spacing we talked about. It's pretty acceptable to just assume that bearing capacity factor, that horizontal bearing capacity factor, is equal to 40. So for depths that are less than 20 feet, we can just assume that we have 40 times alpha B. Remember, alpha B was a factor that's based on the thickness of the bearing elements. This is alpha sub B, which is I'm trying to remember when it's 2 and when it's T. Oh yeah, this is right. I'm sorry. So the alpha B is the T, which is the diameter of the element divided by 2 times the spacing of the elements, the transverse spacing elements. So that just reduces down to 20 times the thickness of the element. The thickness of the element. We don't usually say diameter, because for the metal grids, it turns out to be the diameter of the transverse elements, but for the geogrids, it's really the thickness of the geogrids. We usually use T. So it's just 20 times T over the transverse spacing. When you get deeper than 20 feet, again, when you get deeper than 20 feet, you've maxed out the effects of the vertical confining stress. And this is similar to the tip bearing capacities for piles. When you're calculating the tip bearing capacity for piles, as you go deeper and deeper, the tip capacity doesn't increase with depth, because the failure surface isn't affected by the surface anymore. Let's see if I can say that another way. If you start with a footing on the ground surface, right, and we know as we go deeper that this confining stress at the ground surface increases the bearing capacity because it's pushing down on this failure surface. Well, if you have a pile that's really deep, that failure surface actually wraps itself back around the pile. And it doesn't matter once you get to a certain depth, once you start generating this failure surface like this around, this is your pile, around the pile, it doesn't matter how deep you are in the soil, you're not going to get any more tip resistance. The same thing is happening, whoops. Let me go back to a color Caesar. The same thing is happening in this horizontal resistance. So if I'm pulling this way and I'm generating some bearing capacity on the sides, you know, I'm going to generate some kind of a failure surface around here as I pull this through. Well, for some, at the vertical stress here is going to increase the capacity of that up to some point. And once you get to the point where this failure surface is wrapping around itself, it's no longer, there's a limit to how much you confine it. You're not going to get any additional capacity to do that confining stress. So that's why these equations have these limits at a certain depth. And it really corresponds to an overburden pressure, but the unit weights of the soil don't vary enough, so they basically just limit it to a certain depth. So at a certain depth, you're not going to get any additional bearing capacity due to this vertical stress. So these numbers change. So that's why this goes from 40 down to 20, and this is really this is similar, except it has to do with the dilative behavior of the soil. Okay. So for geosynthetic soil, we usually we base the pullout resistance based on we do it differently. We just assume that we have an interface friction. We're just going to calculate the friction angle of the soil, and we're going to reduce the frictional component for the geosynthetics based on some factor times the internal angle of friction of the soil, because it's easy. So this CI term is generally determined using laboratory tests, but for planning purposes, you can just take that as 2/3 of tangent of the internal angle of friction, which is a nice number, because if you remember when we were picking delta for Coulomb walls, we said delta was, you know, if you didn't know what else to do with delta, pick 2/3 of the internal angle of friction. So I don't know, maybe we're simple-minded, or maybe there's some universal truth that the interface friction for most things we stick in soil compared to is 2/3 of the internal angle of friction. I don't know, but that number comes up a lot. So that's a good place, that's a good number to use for scoping calculations. Again, I think I probably said that 5 times already today. You really want laboratory tests for these things. Laboratory tests cover all your sins. You don't have to worry about whether it was generated through bearing, what was generated. You're just going to do laboratory tests, pull it out, and you got numbers you can really use. So this is if we have only a frictional portion. So before I go on to the next part, let's go back and summarize this, because I think we lose sight of what's going on in the middle of this. So this is our basic equation for determining pullout resistance. Even though the pullout resistance is a function of friction and bearing, we're going to convert those both into an apparent friction term, or if you want, you can think of that as an apparent coefficient of friction. And that's going to be multiplied by the vertical effective stress. The alpha factor is just there to account for whether if we have extensible reinforcement that's going to actually significantly strain, then we're going to reduce the pullout resistance because of that. And then we're just going to multiply by the length that's being the length of the reinforcing element within that's available to resist pullout, and then times 2, because we always have resistance on the top and the bottom. And then we have a real convoluted way to estimate this based on geogrids versus friction. But ultimately, what we really want to do is put the reinforcement that we're going to use in a test device and actually test its pullout capacity. And I think for all the most common design materials that are out there, they're going to give you this pullout resistance as a function of the length and the normal stress. So you won't have to do that really. Okay. I think that's where we were at, right? All right. Okay, so let's talk about soil properties. So I alluded to earlier that there are different kinds of soil here. So let's get our nomenclature straight. We have foundation soil. That's the stuff below the wall. That's usually the stuff that was there before we got there, although you could be working on a recompacted surface. I mean, you could have a case where this is actually controlled fill, but the foundation soil is the stuff that's below the wall. It's going to be important when we do the external stability analysis of the wall, and it's going to be important for global stability, but it's not important for the design of the wall itself. The soil that's within the zone that's reinforced is reinforced soil. It's part of the wall. You really need to think about this as part of the wall. This is like the concrete in your concrete cantilevered wall. We're going to treat this totally different than we treat all the rest of the soil. All the stuff we were just talking about interface friction angles and lateral bearing capacities, that's this soil we're talking about. That's the soil that you're going to use to build your reinforced wall. The soil behind the wall is called retained backfill. That's often also select material, but it's not the material that's. It could be the same material as what you use for reinforcing the soil, but it's a completely different function. This is the material that's actually going to generate the lateral earth pressures on your wall, whereas the reinforced material is the stuff you're actually going to try and calculate pull-out capacities and anchorage length for your reinforcement and all that stuff. So the best way to think about it is, this is your wall. All right? And you have retained backfill just like you do for any other wall, and you have foundation soil just like you have in any other wall. So, but when we're talking about MSE walls, we basically end up with three kinds of soil. You got foundation soil, you got backfill soil or retained backfill, and then you have the reinforced backfill or the reinforced soil. Don't confuse them. It's bad. Okay, let's talk about foundation soils, and then maybe we'll take a break from there. All right, so for our foundation soils, we need the normal strength and compressibility properties like we would for any wall. So we need to know the unit weight. We need to know its strength parameters if it's a cohesionless material, or if it's a drain conditions. We need to know C prime and phi prime. If we're going to need undrained analysis, we need to know the undrained shear strength. We need its compressibility. We can either use coefficients of compressibility, C sub C, C sub R, and the preconsolidation stress. If it's a relatively compressible soil, if it's a relatively compressible clay soil, or if it's a fairly stiff soil, it's probably easy. You're probably better off estimating settlements using elastic methods and just getting a Poisson's ratio and a modulus of elasticity or some other modulus method, and just calculate the settlements based on elastic methods. For those of you in 531, we just had a big discussion about that last quarter. So we're going to use this information for the foundation soils when we determine the global stability, because it's basically a slope stability problem. We're going to need to know the strength of the foundation soil. We're going to have to, even if we don't have a global stability problem, we're going to have to check bearing capacity for that soil, and that's where we're going to use these properties to check the bearing capacity. And the overall settlement of the wall is going to be a function of the foundation soils. When you get information from your suppliers, they're going to give you all kinds of information about backfill material. They're going to one thing they're never going to talk about is the foundation material. They have no idea what foundation you're going to put your wall on. All right? So, and so they will not talk about bearing capacity. They will not talk about global stability in their design methods because they have no idea, and they're not going to take on any liability. So make sure that you're doing this, because this is never going to be in the scope of the supplier of your wall materials. Okay, let's talk about the reinforced backfill material. So this is the material within that zone where you're putting reinforcement. What's important with it? Well, the strength of it's obviously important because it can fail and rupture. You know, we can actually break the reinforcement. This is not an uncommon failure method. Its compressibility or relative stiffness is important. Well, both its compressibility and its relative stiffness. If it's compressible and you get a lot of settlement, you can get settlement in that reinforced soil. So if it's too compressible and you get settlement in there, that's a problem. It's really important that it be a good draining material, just like we have that issue with any walls, is we really don't want to have water pressures behind our wall. So drainage is very important. And then its durability is important. It's just like your any of you that do selection of materials for paving, you know, you don't want soils that slake or have durability problems in pavements because, you know, 20, 30 years later you've got problems because there's loss of material, there's settlement, there's loss of strength, so durability is important. And then one that we don't often think about too much with geotechniques is corrosiveness is very important, particularly for metal reinforcing materials. Not such a big deal for the polymers, but we'll talk about even polymers, there can be some concerns. So the properties that we're interested in are its strength parameters. We're interested in the grain size distribution because the grain size distribution, if you recall from our estimates of the lateral bearing pullout capacity, is a function of the grain size distribution. And what else is a function of the grain size distribution is going to be important to us? What other these are important? Besides strength is clearly a function of grain size distribution. What else is? Drainage. So drainage you want like poorly graded soils, and strength you want well graded soils. But really what you want is just soils without fines in it. So really what you want is a well graded material that doesn't have fines in it. Slake loss is the way we usually check for durability. And then we have to know its electrochemical capacities. That's how we're going to evaluate its corrosivity. And let's see where we're at here. Yeah, let me finish this section and then we'll take a break. Break will be a couple minutes late. Okay, so mechanical properties. These are the general recommended mechanical properties for your soil. So generally you want stuff that's 100% passing the 4-inch. We don't want more than 15% fines in those, and you don't want clay material in those fines. So if you've got up to 50% silty material, that's probably okay. If you've got a little bit of clay, it's probably okay. But what you really want is coarse, fine, small gravel through sands with less than 15% fines. If you're using geosynthetics or epoxy-coated bars, which aren't particularly common, the epoxy coating, then you generally want to limit yourself to 3/4 inch. Otherwise, you tend to damage. The issue with the epoxy ones is you damage the epoxy coating, and the issue with the geosynthetics is that you tend to damage the geosynthetics, which we'll talk about in a few minutes. This is how you make sure that what you have is, if you do have fines, is silts and not clays. By just limiting your plasticity index, you don't need to go do a hydrometer analysis on it. You just make sure you got a really low plasticity index for the fine material that's in there. If you got a PI of 6 or less, then you shouldn't have a problem. You essentially have silty sands then, and you don't have clay sands. If you have a coefficient of uniformity that's less than 4, so if you have a very uniform soil, then you definitely want to be doing laboratory pullout tests, because almost all of the specifications and the pullout tests that are done for well-graded material. So if you've got poorly graded material, you want to be doing pullout tests. So in durability, you don't put shale in there. No shale, no soft minerals. And you'd like the magnesium sulfate concentrations less than 30% and sodium sulfate concentrations less than 15%. And electrochemical properties. So the electrical chemical properties are depending on what kind of reinforcement you're using. If it's steel, there's a lot more issues with corrosivity. So if it's steel, you're going to have to check its resistivity, pH. You can check for chlorates, sulfates, and the organic compounds. And these are these are criteria limits that come directly out of your design guidelines from the FHWA. So we basically want a non-reactive backfill. You don't want to be putting highly active backfills in with metal reinforcements. We'll talk about how we protect the metal when we talk about the reinforcement properties in the next section. And these generally aren't difficult to come up with. With polymers, as you might think, they're much less susceptible to problems. Here's where you need to understand a little bit of polymer chemistry. Or actually, you don't need to understand polymer chemistry, but you do need to understand that there's difference between different kinds of plastic. So all plastic is not the same. And what the plastics that are most susceptible to chemical actions are the polyesters, the PETs, and the polyolefins, which is high-density polyethylene and polypropylene, are less susceptible to chemical degradation, but they're also less stiff than the polyesters. So there's advantages and disadvantages to either. The polyesters are stronger and stiffer, and the HDPE and the polypropylenes are weaker and more flexible, but they're also less susceptible to chemical. This is a pretty freaking low pH, so this is probably something you're not going to run into. This becomes important if you're designing systems for mine tailings, heap leach fields for extraction of minerals. This is about the only time, or some kind of any kind of systems for other kind of chemical processes are going on. So generally speaking, for most wall problems, this becomes a problem more for like liners for systems and stuff in these systems. But if you were designing a wall system that was supporting some kind of a tailings dam, this is something you would really want to worry about. But generally speaking, those are, pH of 9 is pretty frickin' high, and pH of 3 is pretty frickin' low, so you're usually not in that range. Okay. So we finished through the reinforcement soil properties. We're going to talk about the retained backfill next, and we will take a break in between. Okay, so we talked about the reinforcement properties and the reinforced soil properties. So now let's talk about the retained fill. Now we're talking about the backfill material that you have behind any wall. This is the material that you're going to have to worry about behind any wall. So we have the typical concerns we have for that. So this is the material that's going to generate our earth pressures on the wall. So we're obviously concerned about its strength because that's going to control what the active earth pressure is. So we need to know gamma. We need to know the internal friction angle. Generally, we don't like putting cohesive materials back there. That's generally a bad move. If the friction angle is less than 28 degrees, you probably are going to end up with some, well, it's going to drive your design, let's put it that way. It may or may not be cheaper to go find a better material, depends where your borrow materials are. But that's definitely you're getting to the lower bound of good material if it's below 30 degrees. If there is any cohesion, you're definitely looking for low plasticity soils. Now this isn't like the reinforced soil where we basically don't want to have any clay in it, but you definitely don't want a highly plastic material. So the PI limit's not as stringent. Okay, now let's talk about how we characterize we talked about the dimensions of the reinforcement properties from a micro sense. Now we're going to talk about a macro sense and its geometry in terms of the whole wall as opposed to a single piece of reinforcement. So generally speaking, unless we have a sheet like the geotextile, we're going to have we may or may not have reinforcing elements that cover the whole width of it. We can have a grid that covers the whole width behind the wall, but very often we have grids or strips that only cover part of the wall. So that's what we're really going to be talking about. The nomenclature we're going to use, if we use B is the width of a single reinforcing element. So it could be a single strip, or it could be in this case, it's shown here, a welded wire mesh that's of a certain width. SH is the horizontal spacing, so that's the unit spacing. You can think of it as center to center or edge to edge, but it's the units. It's the horizontal spacing of the reinforcing elements, not the space between them, the center to center or edge to edge spacing. If we have, if we're using welded wire mesh, then we use D star for the diameter. It's not necessarily really the diameter. We'll talk about that in a while, but D star is a characteristic diameter of the longitudinal elements, because that's what we're going to use that to discuss the strength of materials. If we have bars, the B is then the width of the bar itself, and SH again is the center to center or edge to edge spacing of the bars. And then the bars are characterized, their area. We have what we're going to call EC. We'll talk about what that is. That's the effective thickness of the bar, and then the width of the bar B. This term coverage is really important. So coverage is the ratio of the width of the reinforcing unit to the spacing. So what's the coverage of a geotextile? Then if we use a geotextile behind our wall, what's the coverage? One, exactly. Right? Because you're going to have a single, you're going to have a single sheet of geotextile. It may overlap, but a single geotextile that's going to have a width of the entire wall, and the spacing is going to be the entire wall is going to be 1. So in other words, that's 100% coverage. And this is important because when we design our wall, we're going to know the loads per unit width of the wall, right? You're going to know force per unit width. You're going to know the active earth pressure per unit width. But we're going to use this coverage term to convert the loads. You know, each one of these is going to have some capacity in each element, right? You're going to have some capacity in each element. And you've got to somehow convert that capacity per element, into the capacity per width of the wall, and that's what you use the coverage for. Okay? Are you with me? Pretty simple concept. Okay, let's talk about the effective area of the reinforcement. Okay, so the effective area of the reinforcement is that area of the reinforcement that's left at the end of its design life. This is particularly important for metal reinforcements, because for metal reinforcements we assume that they corrode and lose thickness over their lifetime. So if you have a round cross-sectional area, the effective reinforcement area is going to be the number of elements per bar, the number of bars per element. Let me go back to this previous one. So in this example, N is equal to 3. So this is a single element, and it has 3 bars in it. So it's the number of elements in the bar, and this is just the area of each bar, except that we're not using the actual diameter of the bar, we're using D star. And what's D star? D star is the nominal diameter of the bar times that diameter that we think we're going to lose over the life of the structure. So we're going to calculate the corrosion rate. We're going to assume how much we lose per year. We're going to assume that, and then we're going to take the design life of it, and we'll figure out how much diameter we lose. Rather than calculating the final diameter, because you usually calculate corrosion rates per year as a thickness lost per time, and so then you just multiply by the number of years to get the amount lost. That's why it has this formulation of the nominal divided by the diameter loss, which initially sounds kind of stupid. But if you realize what we're going to do is we're going to know the diameter loss as a function of time, and then we just multiply by time, we get the diameter lost over the life. For rectangular cross-section, the area is EC times B, where, and we usually, for the bars, because they're usually a whole lot wider than they are thick, when we degrade them over time, we keep B constant and we just worry about degrading the thickness of them. Because it's not, it's just too inconvenient to do it the other way. So, and they're really, you know, the aspect ratio was probably 10 or higher. So it's the B's not where you're losing most of your area. So for the bars, we do the same calculation where En is the nominal thickness of the bar minus that thickness that we lost during its lifetime. So essentially, whenever we do our capacity calculations for the reinforcement, we're going to estimate how much reinforcement is actually going to be there at the end of the life of our structure, and we're going to design for that area. Okay, so let's talk about steel corrosion. This is another case where you again, like I said, you don't need to know chemistry. You need to know that somebody needs to know chemistry, and that chemistry is important, and look it up. Galvanizing, this is the standard galvanizing weight. When you specify galvanizing, it's usually specified in a mass per unit area. Because what you do is, when you put the galvanizing on, they know what the mass of the material is. They stick in a tank to galvanize it, and they know how much weight it had before and how much weight it had after. So it's easy to calculate the amount of galvanizing, not as the thickness of galvanizing on the element, but just as pounds or kilograms per square meter. In fact, it's almost always measured in SI units. This corresponds for most of our stuff to a thickness of about 86 microns or 3.6 mils. So in the mildly corrosive soils, and we know we're going to have mildly corrosive soils because we're going to specify that we have mildly corrosive soils in the backfill. So if for some reason you end up designing someplace where you don't, then you're going to have to understand the chemistry, or get somebody to understand the chemistry for you and estimate a different one. So this is based on the assumption that we're putting these the materials, the reinforced soils, have those specifications that are listed in your design manual, and that we're using zinc galvanizing. There's other kinds of galvanizing out there, but this is by far the most common. You get a different loss over the first 2 years than you get over later. So the first 2 years, because there's defects in the galvanizing and all that kind of stuff, you get greater losses during the first 2 years, and after that the losses slow down significantly. I don't think it actually slows down in a bilinear fashion like that. It's a curve that decreases over time, but this is the way we estimate it. So you're going to assume that you lose about 0.6 mils per year for the first 2 years, and less than a tenth of that for every year after that. So that's how you estimate the losses. And then once you get through all the galvanizing, then you got to calculate the loss of the actual carbon steel, which is much faster. Notice how much faster this is than that. So if you get to the point where your galvanizing is gone, then you got to calculate the loss of the steel itself. So if you're not using a specified low corrosive reinforcing soil, then you need to do your own tests and get somebody who knows how to do them. In marine environments, the losses are faster because you have to worry about salt and salt action and stuff like that. Or if you're in a place where there's roadway issues and there's going to be a lot of salt used in that, there's another place where you probably need to worry about that. And there are certain specifications detailed in that in your design manual. So if you're dealing with places, if you're not in sunny Southern California and there's places where they use a lot of de-icing salts, or if you're in marine environments, then you're going to have faster corrosion and you need to account for that. Okay, let's talk about stresses and loads in our reinforcing elements. I don't know what this, I think this is supposed to be, I don't know what's wrong with that character. I think this is supposed to be a defined. I'm pretty sure that's what that's supposed to be. And I don't know how it got, I just looked at this before class and it was right. So that's what this issue was. You guys probably saw it one back. Where was it? Was it here? This should be defined to be. Sorry about that. Okay, so T we're going to define as the tensile stress in each element. Okay, so T is going to be equal to the force in the element divided by, when I say element now, for a bar it's a single bar, and for a grid, if I have an element, where's a good example? So here's an element that had, if I was using this as an element, it would have 4 longitudinal pieces to it, right? And so the effective area would be the effective area of one element times 4. So it's the total force divided by the effective area of the element. Again, this is defined as and the T is the tensile load per width of the reinforcement. Okay, so T is going to be equal to F divided by B. Let's go back to our figure here. Right? So big T so big T is the load per element, and little t is the load per unit. So little t is the total load divided by the area, right? That's the tensile stress. This is a stress, and I don't like this nomenclature, but this is a nomenclature that your design manual uses. I mean, they use in letters for both stress and forces. And T is the tensile load per width of the element. So this is the force divided by the area. This is the force divided by B, which is the width of the element. Now, so for bars, these are the same thing, but for grids, it's as if if you want to think about it, big T is like the load as if you had the grid all the way across it. So in this case, it's the thickness times the apparent area divided by B. So T star is the tensile load per width of the wall. This is the one we really want for design. When we go to design, we got to know what's the reinforcing force per width of the wall. So I've got to convert, this is why this gets confusing, I've got to convert this load per element to a load per wall. So this is just going to be the load per element times the coverage. That's why we define that term coverage. So this gets very confusing. It's conceptually really simple, but it's easy to screw up, and if you screw it up, you're going to have a bad design. So make sure you understand the difference between the tensile stress and the element. This is going to control rupture of the element. When we're going to check whether we're going to rupture the steel or rupture the plastic, this is what we want to know. What's the stress compared to the yield stress or compared to the allowable stress? Right? This is how we're going to calculate the loads in the elements, and this is how we're going to design the wall. Okay, so let's talk about how we get the allowable loads for the steel elements. So for the steel elements, this is pretty straightforward. We're going to determine the design life and the coating thickness, and from that we're going to compute the area that's left at the end of design. It could be all the if there's enough zinc coating, it could be all steel. But if you eat through the zinc, then you got to calculate the steel, and then we're going to have a T allowable, and it's just going to be this final area times Fy divided by B times whatever your factor of safety is. So it's just yielding of the steel, very simple. Oh yeah, and they use an inverse factor of safety here. Rather than dividing by F, they use, I mean, normally we think of F as a number greater than 1. They multiply by a number smaller than 1. I don't know why it's done that way, but it is. So you end up with this factor of safety, which is 0.55, which you think might look really strange, and at least if you're a geotech, just flip that over and it turns out to 1.8, and so that we're talking about a factor, what we would normally call a factor of safety of like 1.8. So By the way, and this, note real carefully, this is for grids that are used with flexible facing. We'll talk about the issues there in a minute. When grids are connected with concrete blocks or panel facing, we use a lower FS or a higher factor of safety. This is because there's been a lot of failures of these. Initially, there were a lot of failures at the wall-facing elements, and was found to be due to either corrosion issues there or differential displacements at the walls. And so to account for the problems that they're having at the wall connections for steel reinforcement attached to rigid panels, you use a more conservative, let's just say it this way, a more conservative factor of safety. So then if you want to compute, what you're really interested in for your design is T star A, which is the allowable load per unit width of the wall. So that's just T star. This part's T star times your coverage. All right, so let's talk about allowable reinforcement for geosynthetics. Completely different world. A lot more things going on with geosynthetics. Geosynthetics have a tremendous creep problem. If you put loads anywhere near their actual rupture loads, they're going to creep forever, and you're going to, your wall is going to be moved out into the roadway long before it fails. So creep is a big issue. They can also get damaged during installation, particularly during compaction, and particularly geotextiles more than geogrids. There are some concerns about aging. There were really concerns about aging. You know, if anybody's got a car that has a dashboard, you understand the issues with aging of plastics because your dashboard's cracked, right? Anybody have a dashboard that's not cracked? Good. I don't have to call anybody a liar. The aging issues in the ground are much less severe than they are out of the ground, but there are still some concerns. The sort of bottom line for this is early in the geotextile world, there were a lot of concerns about this. There were a lot of testing was done. They felt it wasn't too much of a problem. They didn't really have the data. We've been doing this now for decades, and we've got some good long-term data, and it doesn't seem to be a big problem as long as you follow the guidelines. Temperature can be a problem, but not a problem for most installations in the ground unless there's some reason that you are going to be having elevated temperatures. If you're putting geogrids near where there's some steam lines running or you're in a geothermal area, then you do need to be concerned about that. And then there really isn't a big issue with confining stress, but that can change its behavior. So what we compute is a T star AL, which is a long-term allowable load in the geogrid. And we basically do this by factoring down the ultimate capacity, and I'll show you how we calculate or how we test that in just a minute, by a whole bunch of factors of safety. So there's a creep factor of safety, there's an installation damage factor of safety, this one is aging, I want to say. I think I've got these written down someplace. Oh, there they are. Creep reduction factor, degradation factor, installation damage factor, right? Degradation accounts for aging. Well, it accounts for aging and temperature. Well, it accounts for aging assuming you have normal temperatures. Let me say it that way. And then we put in what we want to call our traditional factor of safety. So the allowable, if you want to think about this part of the equation, is what you do to get down to the usable capacity of the geogrid or the polymer. And then we're going to put in our traditional factor of safety for our uncertainties. So all those other ones have to do with behaviors that we know are going to be potential issues with the polymers. So there's a lot of factors of safety here. In fact, you'll find out that you end up using a very small fraction of the ultimate rupture capacity of these plastics, which is why it's a good thing they're cheap. If this was steel, we would never use it. Which, by the way, is why steel is competitive. So creep reduction factors. So we do what's called a wide width tensile test. So you want to do a tensile test. This is a pretty good example. If you looked at some of these geogrids, so this tensile test is 2 to 3 times the width of some of these elements that I showed you here. So this is on the order of 10 to 12 inches. So it's a wide width thin, because you don't want to, you want to be sure you're getting the properties of the actual whole element. They do creep tests on these things that last, have originally lasted for greater than a year, and then they also do things where they extrapolate out. They also do high temperature testing, and they do do a bunch of things to try and extrapolate this out to decades and decades of behavior. And so here's the bottom line. This again comes out of your design manual, but look how large these creep factors are. So if you're using HDPE, you're already down to 1/4 to 20% of the capacity of the ultimate capacity of it. This is why these things are so resilient in like in earthquake loads and all this other kind of stuff, because you're using a very small fraction. And notice how much higher the reduction or how much lower the reduction factor is in polyesters. This is why polyesters are popular, because they're much stiffer and they have much less creep characteristics. But also remember, they're the ones that were most susceptible to chemical action. So that's the disadvantage of the polyesters. And that's why some of these, I showed you some of these woven ones that were these grids where you can put different materials. So some of these are a combination of HDPE and polyesters that they try and optimize both characteristics. It is kind of black magic about what actually goes into these things. I mean, you know the basic constituent of them, but you don't know exactly how they manufacture their plastics. So it's really important that you get the performance data from the manufacturer. You need to make sure you're using the performance data from the manufacturer for the material that you're using. Don't mix and match. Don't say, oh, I got HDPE data, I'll just use it. Don't do that, because it's not all the same, and it's all proprietary. You're not going to know what they're doing. Provided by the manufacturer. Durability factor. So the durability accounts for chemical degradation, biological degradation, and thermal degradation. The thermal degradation is assuming that it is installed in normal material. So if you're in places, again, with high elevated temperatures, you're going to have a higher degradation factor. So they basically oxidize, they take this material and they put it in an oxidizing environment, and they elevate the temperatures, and they basically oxidize it in an accelerated fashion and try and use this to estimate the amount of degradation occurred during the lifetime. We call this the durability reduction factor. It's relatively small. It can get up to 2, but you can tell this is way less than the creep reduction factor. You have recommendations for polyesters given in Table 9. For polyolefins, including HDPE, it's really dependent on the manufacturer, so you need to get that data from the manufacturers, because they put pixie dust and dragon spit and all kinds of little strange materials in their plastics and make them perform differently and better, and the only way you're going to know how it's performing chemically is from their data. So I just said that. Installation damage. So this is going to be a function of the backfill, how you backfill, and the materials. This is one of the reasons for the geosynthetics that that we're using plastics for the reinforcement, that we limit ourselves to 3/4 inch stuff, because you get the bigger stuff and you tend to get a lot more insulation damage. Where with the steel, that's not such a big deal. So if you got a situation where you're going to be having gravel and very large reinforced soil materials, then you want to be using steel. So backfill particle size and shape. Obviously, if you got angular material, you're going to get more damage than if you got well-rounded material. And how you place it. Larger backfills increase the reduction factor. The slit films, I didn't discuss it. There was a slit film here. If you look at the if you want to come up and look at this afterwards, if you look at some of the slit film, those plastic tarps that you get, that you use for everything, the blue ones and the green ones, they're all slit film. Look at one of those sometimes. If you look at them, you'll see that they're actually woven out of very thin, wide elements, relatively speaking. And they're called slit film because what they do is they take a film like a garbage bag film and they slit it, and then they weave it. And so they're called slit films. They're the most susceptible to damage. And these HDP geogrids, like these big, thick tensor ones, are the least susceptible to damage. And Typical again, these are relatively low compared to our reduction factors for creep. But generally ranging from 1.1 to 2. You have a table in your design manual that gives you some examples, and again, the manufacturers will give them to you. This stuff is basically determined by going in and exhuming stuff after, they do test fills and film, and they go exhume it afterwards and test it afterwards, and use that to estimate the damage elements. And then we use a factor of safety. This is to cover all the rest of the sins that we commit during the design, build, and construction of these things. So generally, a factor of safety of 1.5 is adequate. And I think I've got an example in here. So let's assume we have a creep reduction factor of 4, a durability factor, a reduction factor of 1.5, an insulation reduction factor of 1.2, and an overall factor of safety of 1.4. You are going to be using 1/10 of the ultimate capacity of your polymer. That's good and that's bad. That sounds incredibly like you're incredibly inefficient. Well, they're incredibly cheap, but they're also incredibly resilient because there's a lot of excess capacity in a sense, short-term duration capacity. That's why when we get to the design of these, you'll see for earthquakes, we use very low factors of safety for earthquakes. They're very durable during earthquakes. So there's good and bad to that. And I'm hoping I'm really near the end because now I've BS so long that I'm behind schedule. So let's talk about the facing elements really quick. So the function of the facing element, the average person in the street does not understand that the facing element is not holding up the wall. The reinforcement is holding up the wall. The facing element has several important functions. One, it has to retain the soil that's at the face of the wall, because if it doesn't, you're going to start having erosion, and eventually you won't have a wall. So it's one of its main functions is to retain that soil near the face. It has to provide some connection between the facing and the reinforcement. Sometimes it's really simple connections. Sometimes it's fairly complicated and proprietary. And then it's got to look nice. That's one of its main functions, is to look good. So there's a bunch of types. There's masonry units. You've seen these. You can go to Home Depot and buy these. Ready Rock. What's the really common one? I can't think of the name of it. I was just emailing the guy today. Anyway, you can go to Home Depot and get these things. Precast concrete units. Those are basically large masonry units for the most part. And we looked at, remember we looked at, when we were looking at bin walls, we looked at T-walls and some of those other, in fact, you can do this with gabions. You can put gabions as the facing material for an MSE wall. Oh, and I just said that. How about that? I love it when I'm on a roll. You can wrap the geotextile around the face of the wall. That's kind of an ugly facing, but you can shotcrete over that. This is a real common method used for expedient construction out in haul roads in the mountains and stuff. And military loves to do this, when we're in the middle of nowhere and they want to make roads and they need reinforcement. A wrapped geotextile face works great. And then types of connections. We can have pin connections where basically you've got little pins that come up between your geogrid if you got a geogrid. For the bars are often bolted to elements that are cast in the face of the wall. For the masonry units, sometimes you just depend on friction. All you do is you slap your reinforcement material between two lifts of the masonry and put the masonry unit on there, and you're depending on the friction between the two masonry units to hold it in. And for medium height to low walls, that works fine. The connection details are important. There have been a lot of failures of walls that are due to poor connection details. So if you have proprietary connections, in fact, all the facing manufacturers will give you specifications for the connections. You need to follow them. I just think I said all that, right? Questions? Cuestiones? Pregunta? Yeah, Jack. The connection between the facing and the reinforcement. A lot of the reinforced earth, reinforced earth is a proprietary term for these T-panels with the little strips behind them. We've seen pictures of them. I was going to find them, but I'm late. I won't find them now. They had problems with their connections in some of their early designs and corrosion at the connections, and that's where they failed. So now you got a wall, you got a facing unit that there's nothing holding the facing unit. The facing unit falls out. Now the wall starts eroding behind the facing unit. Did I answer your question, or am I'm looking like you're looking like I'm not asking?
Also, the wall actually doesn't fail.
No, they've had wall failures because of that. Oh yeah, yeah. They had a wall failure down in this overpass of the 71 here, where it's not Valley, it's the next one down here. They just built a big MSE one. They had a wall rupture there. They had a failure at that one, and it was a facing problem. Connection to the facing. It's really, hey, structures guys, where do things always fail? Where do buildings always fail? At the connections, right? Connections are dangerous places. So we looked at some of these. Maybe next time, we got some time next time, I'll bring back some pictures of the connections and we'll go, because probably when we looked at them before, you were just like being overwhelmed by the massive amounts of pictures I was showing you. So we'll look at some of the facing connection details that I've got. I've got photographs of those.